All right, good afternoon, everyone. Let's start. By the way, don't forget our homework 1 is due on this Friday, if my collection is correct. So I've seen a few questions posted on Canvas about homework 1 problems. That is great. I mean, if you have any question you want to seek for help, please do not hesitate to come to this office hours or ask questions on Canvas. Okay, let us continue with the generalized linear regression, generalized linear models. So in the last lecture, we introduced the general definition of the so-called Bayesian linear regression, but it's not truly a linear modeling, a linear relationship between the input features and output, because we can define a set of bases, right? A nonlinear basis. Those nonlinear bases are kind of feature mapping or feature transformation from the original features. So those feature mapping, the definition is totally up to the users, right? You can define the feature mapping as some Gaussian densities or neural network output, whatever, right? So in that sense, the commonly used like feed-forward neural network can be viewed as a special case of Bayesian linear models. So so that means this family of Bayesian models is actually quite expressive, right? It just preserves a high-level linear modeling structure, which does not necessarily mean that the final relationship between the input and output is really linear, right? So we talked about, suppose we assign a prior over the weights, right, which corresponds to a regularizer. Right? We talk about what is regularizer, right? Why should we use regularizer? Like, for example, if we just use a Gaussian prior over the weights, we have some prior mean, prior covariance, and given the weights and also the input features, we're gonna generate the output from this linear model. So you can see it's a Gaussian model, right? So the mean is defined as the design matrix phi times the weight vector W. So remember, phi is n by d matrix. Right? Let me write it down, right? Phi is actually n by m matrix, where n corresponds to the number of the examples. Right? Each row corresponds to one example, and each row consists of all the mapped features or nonlinear basis for a particular example. Right? Then we multiply with this weight vector, but we assume the observation is not really accurate because many real applications, the observation is always corrupted by some noises. That's why we use this Gaussian likelihood, and this noise variance is modeled by this inverse variance beta. And then if you just multiply the prior and the likelihood, we can calculate the posterior distribution of the model weights W given the training data, right? So here, the bolded T just indicates the observed outputs from the training data, which is another Gaussian, right? So you can simply use completing the square trick we discussed before to obtain this posterior Gaussian form, which is relatively easy, but we highly recommend you guys to manually verify the form, right? So a simple choice for this model is that, okay, we just choose M0 to be 1, right? S0 to be identity matrix skewed by some constant alpha inverse, right? And given this likelihood, and we can calculate the posterior distribution, posterior mean, and posterior covariance. And also we used one example to showcase how the posterior distribution of the model weights vary along with more and more data have been observed, right? So that's just to give you a sense how Bayesian learning are updating both the model parameters and your beliefs about model parameters gradually, right, with more and more data incorporated. So we highly recommend you guys to go through these examples, and if you feel it is not enough detail, just to check out the PRML book, right? There's 1 or 2 pages that give a very detailed explanation of those figures. And then we talk about the general Bayesian prior, which gives different types of the regularization effect, right? If we choose Q here to be 1, it goes to the so-called Laplace prior, which corresponds to a lasso sparse regression technique, which are used like for decades. If Q equals to 2, it is called Gaussian prior. Okay, now I want to talk about something which the frequentist methodology cannot provide, which is called predictive distribution. This is unique for Bayesian guys. What is predictive distribution? Remember, in Bayesian viewpoint, we will the model parameters, namely the weights W, as a random variable. So it has a prior. In our case, we just assign Gaussian prior. And as Gaussian likelihood, so we can calculate the posterior distribution of this W given the training data, right? So that means we actually have a bunch of a set of different weights to make the final prediction, right? So if you do it do the map, if you do MAP, right, like in frequentist point of view, or just a maximal likelihood estimation, you only got 1 point estimate of W. Right? You only have that choice to make prediction. But now, if you use the Bayesian's methodology, you're gonna get a posterior distribution over W. Then when you make a prediction for a new output, right, a natural idea will be, okay, why not just integrate all possible predictions made by different W across this posterior distribution. We'll integrate them together to give our final prediction. In this sense, we hope that our prediction will be more accurate, will be more robust. So that's the idea or the motivation of the predictive distribution. Right? So the predictive distribution is defined as the posterior distribution of your prediction given the training data and possibly given some hyperparameters. So remember, alpha corresponds to the inverse variance of the prior and beta corresponds to the inverse variance of the likelihood. Right? Suppose alpha beta here is fixed. Right? So you can see that this predictive distribution or posterior distribution actually does not contain W. In other words, if you want to compute it, you need to integrate out all the W or marginalize out all the possible W. Right? So how do we do that? Right? So essentially, we can first consider the joint posterior. The joint posterior of your prediction and the model parameter W given the training data. So here the T tilde here just indicate bolded T, right? And I'll also have parameters. Right? So we just marginalized out this posterior, joint posterior distribution, marginalized out W. Right? So this joint posterior distribution can be further decomposed as the posterior distribution of W itself. And then given W, what is the distribution of T? That is prediction. So because once your W is known, your prediction is fixed, is known. So actually is independent to the observation or the data given W. What's your question?
Most of the times, the signal is intractable.
Yeah, of course, it is intractable.
So is a syntax intractable sometimes?
For this particular case, like Bayesian linear regression, it is tractable, but in most cases, it's intractable. I mean, this is just to define what is predictive distribution. But in practice, well, when you use a variety of models, in most cases you have to approximate this. But here, let us start with the trackable and simpler case. So that means this joint posterior is decomposed as the posterior of the W given the training data. And then given W, what is the distribution of the prediction, which is just a Gaussian. This is a Gaussian, this is a Gaussian. So you can see the first guy, the likelihood is Gaussian, And this guy is a posterior distribution. I'm sorry, I need to erase this. So again, see that the first and the second distribution are both Gaussian. So you just do their integral is another convolution of Gaussian. So that means this integral or marginalization is analytically tractable, which turns out to be another Gaussian. And here we just list the form here. We won't be able to, due to the time limit, we won't be able to show how you derive this, but by leveraging the completing the square trick, it will be pretty easy for you to obtain this final form, and we suggest you to practice, because you see that in Bayesian learning, such kind of Gaussian convolution, Gaussian Gaussian multiplication, and so normalization, those kind of things are very, very common. So this trick is also very useful. Now, similar to our previous example, right? I want to showcase some predictive, some concrete example to give you a sense how the predictive distribution varies with more and more training data incorporated. Which notation? What? Alpha here is the inverse variance of the prior. Okay? So beta here is the inverse variance of the Gaussian likelihood. So actually, you can view like alpha determines how wide your Gaussian prior will be, right? Beta actually indicates, okay, how noisy the observation will be, right? Because beta indicates the noise, inverse noise variance. So, and here we give a concrete example of learning a sine function with 9 Gaussian basis functions. Basically, you can view like each basis is a Gaussian density with different mean and variance. So, and these green curves are the ground truth. And the blue circles are training examples or observations. And the red curve is the mean of the predictive distribution. It's here is Mn phi x. And also we draw that in this input range, right? At each point, we just calculate predictive variance, which is given here. We can see that, I mean, the shaded region indicates the predictive mean plus or minus the predictive standard deviation. So from that, you can see how uncertain your prediction at different input. Okay, we can say first, when we only see one example here, right? So your predictive mean is almost a line, a horizontal line. Of course, it didn't really capture the function itself, because your training data is so little, right? It doesn't provide enough information. And also, your predictive variance is pretty large, right? Except that surrounding the training points is relatively smaller. So now, if we add one more data point, things get a bit improved, right? First, you can see some curvature of your learned predictive mean, meaning that it kinds of like a get changed toward to the ground truth, which is this green curve. Right? At the same time, in more areas, you kind of reduce the predictive uncertainty quite a bit, right? But it's still far from the ground truth. With more and more data points added, right, you can see when we add more points here, you further get closer to the ground truth, and at the same time, you largely reduce the predictive standard deviation or predictive variance. Right? And finally, if you add a lot of data points, like 20 or 30 circles here, so you can see that the predictive mean itself is quite close to the ground truth. Right? At the same time, the predictive uncertainty is largely reduced, right? And is much more acceptable. And you can imagine we will add more and more data points. We should be able to see some overlapping between the predictive mean and the ground truth, and at the same time your variance, the predictive variance is reduced to be very, very small. So this is kind of consistent with what we have observed in our previous case, where with more and more training data added, your posterior distribution over the model parameters is kind of more and more concentrated, right? Meaning that you are more and more certain about those where those parameters locate, although you still include some uncertain information. And similarly, if you draw the model parameters from the posterior distribution of the model parameters, right, and then shove into your linear model. Remember, this linear model is defined as a linear combination of 9 Gaussian bases. Right? So it is essentially not a linear function, but it just has some linear structure. Right? So if you only have observed one data point, well, you can imagine your posterior distribution is quite wide, right? Quite wide, and then you sample W from all kinds of places, so end up with those widely spread function curves. We have 2 more points. Your posterior distribution is much more concentrated. So when you sample them from posterior distribution, then use them to construct the function of Y. And so you can see the range is much more narrow. Right? And you can continue to do that. And we will see a lot of training examples. We can imagine the posterior distribution is very, very concentrated, right? So we sample a lot of W. Those W are quite close to each other. And correspondingly, the function of Y is quite similar to each other, right? And also quite consistent with the training set. Now, let us talk about model comparison. Suppose we have a set of models like M1, M2, M3, and 100. This is pretty common, right? If you want to address one particular problem at one particular data set, you always have some choices, modeling choices. Should I use decision tree? Should I use random forest? Should I use neural networks or SVM, and so on, or logistic regression? You have a large number of models which are available, right? So then a natural question will be like, which model should we choose, right? Which model is better for this particular application? There's no answer that one model will be better than all the other models across all applications. It's actually not like that. It's very possible, like in this particular application, on this particular data set, SVM is better, much better than neural networks. And in other scenario, it might be that the neural network is pretty dominant over all the other methods, right? So how can we conduct model comparison in the Bayesian framework, in the probabilistic framework? Mm-hmm. It's not Gaussian process. Okay, I briefly just because this is talk about the conceptual level. What is Gaussian process? So Gaussian process essentially assign a prior over functions. It's not over some finite models. So when you see the computation, well, because what you observe is just the finite data points. You have observed 100 data points, 1,000 points. You cannot observe infinite number of data points. So what you say from a computation perspective is just a finite projection of Gaussian process. But if you want to understand Gaussian process, you should view it as a functional prior. It's a prior constructed over functional space rather than some a real space. Yeah, we'll get to that because Gaussian process is definitely one topic we want to discuss more in detail. But if you want to know more, we can ahead of that we can discuss more in detail after class. Any other question? Okay. So yeah, so to perform Bayesian model comparison, of course, we need to talk about what is prior, what is likelihood, right? So we're assuming, okay, this particular data is generated by one model out of these L possible choices, right? So which are not sure. So of course, we can assign a prior over the ground truth model, right? So we can assign a prior, given our prior belief that the ground truth model is MI, right? And if you have a finite number of models, well, you can put a discrete or categorical distribution over those models. And then, given a particular model, naturally, we can evaluate the probability of the data generated by this model, which is called likelihood. Right? So you can see this is kind of similar to what we have done for general Bayesian model, except that what we operate on is the models. So then, following the Bayes rule, we want to compute the posterior distribution of the ground truth model is MI given the data D, okay? And is proportional to the our prior beliefs that model, the true ground truth model is MI, and then the likelihood that given the ground truth model is MI, the data is generated, right? The likelihood of the data. So the latter is called, this guy is called model evidence. The model evidence is just the marginal probability of the observed data given this particular model. So we can view like the larger the probability, the strong evidence showing that, okay, this data is indeed generated by the model. If it is very small, you can say, okay, the evidence is quite weak. So in general, if we don't have like strong preferences over each model, you might just view this P of MI is uninformative or uniform, right? So if it is just L is finite, which this is just might be uniform. Then if you want to compare a model, you're essentially comparing different evidences, right, for different models. No, it's not like that. That's the amazing property of the so-called model evidence. It doesn't. Yeah. I'm gonna talk about it right now because that's why. In theory, we can maximize model evidence to select the proper model. The model evidence doesn't necessarily favor more complicated models. It's gonna give some penalty over complicated models. Yeah, that's something amazing. I mean, although on the first side you will see, okay, this model evidence seems to prefer more complicated models because they can fit data well. But here, because you can imagine the model actually consists of many parameters, and here we are talking about the marginal probability of data given that model. Meaning that you have to integrate out all possible parameters within that model. So because of this integration, you see that it includes some mechanism that penalize overcomplicated models. I mean, it's not like the more number of parameters you have, the better you have model evidence. Okay, so so to compare different models, right, in terms of evidence, we can just compare the ratio. This is called the Bayes factor, right? And also, given a bunch of models, some other people might think about why not we just give up all the other models, right? Just pick one, right? Why not we just leverage every models? So that means we can use those L models together to give our final prediction. So it's called a model error region. So you can view it as a Bayesian version of ensemble. But this ensemble prediction is also done while basing a probabilistic framework. Why? Because you can say, if we want to give the final predictive distribution, give a final prediction, a predictive distribution of the prediction, right? Of the prediction given this test input, given this trained data, right? So we essentially view it as the marginalization of this posterior distribution of the prediction and the model given of test input and the training data, right? So this joint marginal distribution can be further decomposed as the posterior distribution of the model itself. Then given the model, what is the predictive distribution of the given test input? So you just marginalize out because we usually assume, okay, you have a finite number of models. So this marginalization essentially is a summation. So this is the Bayesian framework to perform model error region. But for other scenario, you might what people are doing, okay, I just train 10 models, right? And I make prediction by each model, I just average them. But you can see that from Bayesian framework, it gives a more elegant way to integrate them together. Yes. I would say I wouldn't say like 100% sure, but in a lot of cases, this will be better than a single model. Like if you take a look at Kaggle computation, many Champagne algorithm models, they involve ensembles, right? They train like a collection of models and do the average, but they essentially doing some Bayesian model average, right? And when we talk about Bayesian neural network, we'll talk about dropouts, right? And dropout, Google even filed a patent for that. They don't want other companies to use dropout to improve their performance. But one explanation about why dropout can improve the performance is that it essentially performs a model average in the Bayesian framework.
So we have two nested Bayesian. I think that when you are trying to compute even the model, to the Bayesian, yeah?
Could it be what?
It could be sitting the Bayesian model, yeah? And also we have a trial on the model selection.
Yeah.
So we have two nested Bayesian, yeah?
Why do you think it's nested?
Because if you just consider we have only one model. For example, we are working with the calcium model. So we have a trial on the.
Oh, you have two models. Yeah. You have I mean, in general, you need to assume, okay, the prior over the models itself. The other, you have like different models. Right. Yeah.
For each model, we have a trial on the parameter of that.
Yeah, that belongs to the particular model. Yeah. But for the prior level, I mean, in practice, people usually assume, okay, each model has an equal chance. It's possible. Right? This is most convenient choice. Oh, for non-probabilistic models, you have to convert it to a probabilistic version if you want to do this in rigorous Bayesian framework. But but in practice, I mean, people won't do it in a strict Bayesian way. They just assume, okay, this is my prediction, right? This is my prediction, and they just average those predictions. But if you want to explain it, you can view as a very rough, very coarse version of Bayesian average. Any other question? And by the way, this is just to give you a framework. Again, it is not easy to compute this posterior distribution. Right? So in practice, it's very likely that you have to involve all kinds of approximations. We're going to talk about like variational approximations. Like sometimes you even have to use Monte Carlo approximations, especially your you have a family of models which are indexed by some real parameters, right? Meaning that they are not simply finite. It's just, it might be integral. And in that case, you might have to perform some Monte Carlo approximation. But anyway, we're going to talk about computational details later. Here, just give you a concept. And of course, sometimes we just want to do the model selection. Right? We just want to find out which model is the best fit for this particular application. I just want to pick up that model alone and retrain to make a prediction. So how can we do that? Right? If we just assume, okay, your prior preferences over the model is equal, like equal for each particular model, then the remaining thing will just to maximize the so-called model evidence. And we will see that the maximizing model evidence relates to the so-called type 2 maximum likelihood estimation or empirical base. So why does the maximization of the model evidence itself can help us select models? So someone has expressed the concern, right? Looks like more complicated models will give a better, larger model evidence. Right? So now we want to give a analysis based on pretty crude approximation to show that actually model evidence is very good. Is a very good measurement. Considers the trade-off between data fitting and the complexity. So how can we make this analysis? We're gonna make a very crude approximation. Okay, so we assume both the prior and the posterior are kind of flat, but the range are different. So the prior, which are indicated by this blue line, you can view as much wider, right? But we can roughly view as a kind of like a uniform distribution, and the posterior distribution is centered around at its map estimation, but with some smaller range. So we can denote the range for the prior by this lambda or triangle or lambda. It should be called big lambda W prior, and this big lambda W posterior. Right? So we make such kind of assumptions just for convenience. But you can see that even with this very crude approximation, we can see some structure inside the model evidence. So let me emphasize again, right? The prior will be something like that. W prior. The posterior, given data, is just something at another range, which is here is a posterior. Okay. So, and then if you calculate the model evidence, the marginal probability of data, it can be approximated written as the likelihood of the data given the map estimation times the ratio of the ranges between the posterior and the prior. Why can we see this point? This is just leverage the basic rule, right? So remember, the posterior distribution is equal to the prior times the likelihood, right? This is a posterior. So now, if you want to get the evidence, you just divide the joint distribution in the numerator by the posterior. And then you get this. So now, if you take a logarithm, we see that the log model evidence is approximately the log likelihood of the data given map estimation plus the log ratio of the ranges, right? One for posterior and one for the prior. And here we're gonna make a even sounds a little bit crazier assumption that suppose our model includes m parameters, and each of parameters has similar property, meaning that each of parameter, the prior is centered around a wider is a flat around a wider range. The posterior of that parameters is centered around map estimation with a smaller range. So if you plug in this analysis framework and given m parameters and assume this ratio is the same, then our model evidence is approximately the log likelihood given the map estimation times m, right? Because you have m parameters. So I have m ratios, m times this log ratio. So first, our observation is that because the posterior is much more concentrated than the prior, right? So this ratio should be less than 1. If you take a logarithm, the logarithm will be less than 0. Right? So now you can see, actually inside the log model evidence, it consists of 2 components. Right? And these 2 components exhibit a battle against each other or some kind of trade-off. How can we see this point? Imagine you have a complicated model, means that you have a large M, like a neural network contains 1 million parameters. Right? So you can expect that given the map estimation of neural network parameters, this log likelihood of the data will be quite large because it fits the data very well. At the same time, because the large M here, remember this is a negative number. The larger the M you have, the smaller number here you have. Right? You can actually subtracting a larger number. Right? So overall, the whole summation, which ends up with the final evidence, is not necessarily very large, because you increase m. On one hand, you increase the log likelihood. At the same time, you decrease the second term, okay, which penalizes over complicated models. So X is trade-off. And then, if you maximize the log model evidence with respect to the number of model parameters, we actually are finding the best trade-off for the data fitting, which is the first term, and the model complexity, which embodied in the second term. That's amazing property when you involve the posterior distribution, the Bayesian framework into the calculation of model evidence. Because in the frequency point of view, well, you only care about this first term, right? It is very easy to encourage complicated models if you just care the data fitting term. And if you want to penalize model complexity, well, you have to intentionally add some regularization, or you have to do some cross-validation, some other things. I believe everyone is familiar with that, right? But if you put it in the Bayesian framework, this procedure, this trade-off are performing in an underlying way. It is automatic. So maximizing evidence naturally leads to a trade-off between data fitting and model complexity. So here is just some kind of visualization to give you a sense. So the x-axis indices different data sets. Might be indexed, might be in terms of the size of data. So you can see that different data sets, even in terms of sizes, might be appropriate to different types of models. Like when your size of data to be small, you might in favor of a simpler model, right? Not that complicated model, because you have a very complicated model, you kind of a larger penalty over the complexity, right? But when you have a very large data, you might prefer a more complicated model, like you have 1 billion images, right? You might want to create a 250 layers of ResNet on that. Although it might contain 1 million, 2 million parameters, it doesn't matter because your likelihood scale is very large. It contains a lot of data, right? Even my penalty term tends to decrease a lot as well, but the first term still dominates. So, and in any other data set, you might just maximize the evidence, which gives you the best trade-off. Okay, so now let us try to leverage this evidence maximization idea, right? Suppose your model family is indexed by some hyperparameters. Like in our Bayesian linear regression case, right? Each particular model can be indexed by alpha and beta. Remember, alpha is the inverse of prior variance, and beta is the inverse of the noise variance. And you can imagine the smaller the alpha, the larger the prior variance, so the flatter the prior, right? And also the beta here indicates the how noisy the observation could be, right? So it actually defines different types of models, and the whole model family is indexed by alpha beta. You can imagine, okay, there could be like an infinite number of models in this family. So, and then the question is, how can we select alpha and beta, set a particular alpha beta, right, which gives the best model? So our idea is gonna to maximize the evidence itself. So that means you just calculate the model evidence given this alpha and beta. So I'm showing that before, right? This is essentially the predictive distribution. It's here, right? We marginalize the model parameters, leaving only alpha and beta here. This is the likelihood of beta, which does not contain the model parameters, right? That means this is the model evidence given alpha and beta. So now we just maximize this model evidence. We got a profit alpha and beta. So this is called type 2 maximal likelihood estimation. Why is it called type 2? Because we have marginalized out the model parameters themselves. We just maximize the hyperparameter which index this model. And standard maximal likelihood estimation will be, okay, I'm gonna maximize both the model parameters, right? Given the hyperparameters, right? We just maximize this, like say MAP, right? It is proportional to the prior of W and the likelihood of data given W, right? But for type 2 MLE, we're gonna marginalize out this W. We'll only maximize with respect to alpha and beta. This is also called empirical Bayes principle. It's very widely used. Any question regarding this? Difference between standard MLE and type 2 MLE. Yeah, it's still prediction. Oh, sorry, no. It's still is observation. It's observation. It's not prediction. So let me restate it. So here, T is the observation. T is the training data, training output, right? So if we perform standard MLE, you're gonna maximize this guy, right? So you're gonna maximize the joint probability of the model parameters and the observation, right? Observed output. This is what I'm doing. We have done, right? So this is proportional to prior times the likelihood of your observation given W, right? This is the standard MLE. So now the type 2 MLE means that, okay, I'm gonna marginalize out W. Right? I only have the marginal distribution of the observed data given alpha and beta. This is called model evidence. This is model evidence we just mentioned. Right? We just maximize this guy. Does it make sense? Okay. So in our Bayesian linear regression, this is pretty easy to marginalize out. Okay. We haven't shown that before. Okay. And you maximize it, and with respect to alpha beta, when you find the best alpha and beta, you actually select a particular corresponding model, corresponding particular model. So this essentially can be viewed as approximating the predictive distribution by assuming your alpha beta are just some point distribution. How can we see that point, right? So if we want to calculate the predictive distribution, right? This is some prediction, right? This is our training data, right? So previously we preserve alpha and beta, right? We assume alpha beta is known, right? So if alpha beta is unknown, well, in the full Bayesian framework, you have to marginalize alpha and beta as well. So that means you have to do an extra integral with respect to alpha and beta, right? So you have the posterior distribution of alpha and beta given the training data, then given alpha and beta and the training data, the posterior distribution of the model parameters, and then given the model parameters, the distribution of the prediction, right? You have to marginalize all those guys. But usually this guy is very hard to compute. Right? So a practical compromise will be, okay, I'm not gonna give up the posterior distribution of W. Instead, we're gonna assume, for simplicity, this posterior distribution as a point distribution. Or you can view, okay, it is just a delta distribution. Right? We just have point mass on a single point. And then if you assume this is just a delta distribution, we'll do the integral. Actually, you just replace alpha beta by the point they have the probability mass. And then you only leave the integral with respect to the model parameters W. And they use this approximation to calculate the full predictive distribution. So this is a very widely used technique in programmatic Bayesian applications, because it's really extremely hard to get all the posterior distributions. So you have to compromise something. Okay. Any question? Okay. So now I want to show, if you apply second type 2 MLE, or maximizing model evidence, right? How does it compare to the effect of cross-validation? Right? So we know that if you do a model choice, the most simple approach is to do a cross-validation. Right? You got the same training data set, and you got some validation data set, right? Just partition the data into many folds and do cross-validation, and to determine which model gives the best generalization performance. This is cross-validation, right? But this is pretty costly, right? But if you just performing type 2 MLE, or that means you're just maximizing model evidence with respect to the model index. Right? So here we use the polynomial regression. So the model is indexed by the highest degree of polynomial regression. So you can imagine if m equals to 9, that means I'm going to use 9 polynomial bases with degree from 1 to 9. Right? So of course, we want to choose the appropriate highest degree to say which model can give us best generalization performance. So we have a large test data. We have the same training set, right? If you just evaluate the generalization performance, we just need to look at how the test error varies along the increase of m. Right? So so you can see that actually when m choose 3, that means you at most need 3 polynomial bases. It can give you the best generalization error. Right? If you keep increasing at some point, your generalization error will be very bad. Right? It will be very large. And if we maximize model evidence in terms of m, right? This is the log model evidence for different choices M. So you can see that this is consistent with our observations. So here when M equals to 3, you give the highest model evidence. That means you just use 3 polynomial bases. Is enough. Okay. Now let us talk about. We have finished the discussion about linear models for regression, and now we're gonna switch to the linear models for classification, because in practice we not only need to predict continuous values, but we also want to make classification. Right? So we're gonna first consider the binary classification problem, namely that we have 2 possible categories to label each instance, C1 or C2. And we'll first introduce the very commonly used logistic regression. So logistic regression defines a model score. So the model score is kind of a prediction score. It's the same as our linear regression case, where it's just a linear combination of set of bases. Right? So this phi is you can view as a set of basis functions evaluated at the input features. Of course, you can also, if you don't want to incorporate any nonlinear basis, you can just assume phi is the original features. That doesn't matter. It's the same framework. So once we got our prediction score, we use a sigmoid function or logistic function, right, to transform this score into a range between 0 and 1. So we model the probability this instance has labeled C1 as this transform probability. So the definition of logistic function is like this. So from the definition, you can see that no matter how you choose A, the range of the sigmoid function is always between 0 and 1. So it's a valid probability. So we're going to model this probability as a sigmoid of our linear model. And correspondingly, the probability of this instance taking C2 will be 1 minus the probability it takes C1. Right? There's one interesting property of the sigmoid function. That is, if you take the sigmoid function with respect to the input, it is sigmoid times 1 minus sigmoid. That's a very useful and very nice property. You can double check with that. It's very easy to verify this. So now let us look at the learning. Right? So obviously the learning essentially is to identify the model parameters W, right? Because the phi is given. Right? Once your basis function is given any input features, you get phi, right? And the problem is that given a bunch of observations, instances, and labels, how do we identify the weights W? Right? So suppose we have a big N observations. Right? So each input feature vector is denoted by phi n, and the output, which is labeled, is either 0 or 1. Right? And we assume they are IID, so their likelihood. So here, bolded T consists of all the particular label. Right? Is the product of the Bernoulli distribution, right? So each term in this product is yn to the power of Tn, 1 minus yn to the power of 1 minus Tn. So yn here is the probability, which is the sigmoid of your prediction score. Okay. If your observed label is 1, then it takes the probability of 1, right? Otherwise, it takes the probability of 0, which is 1 minus 1. So don't get confused here. Yn here denotes the probability the model predict this instance n to be labeled 1. Okay. So Again, we can start with the basic framework, which is maximal likelihood estimation. Okay? And to estimate the model parameters, if we follow the maximal likelihood estimation framework, we just maximize the log likelihood, right? And in other words, it is equivalent to minimizing the negative log likelihood. But they are same thing. If you take the negative log likelihood, it will give you this form, right? And then to maximize to minimize the negative log likelihood to find optimal W, we just take the gradient, right? You want to leverage the gradient information to optimize W, which gives this, right? So, of course, you can just shove this gradient into any gradient-based optimization approach. It will help you estimate W, right? But here we're going to introduce a more efficient and more commonly used approach for MLE estimation of logistic regression, which is called iterative related least square method. Right? This is essentially a second order optimization method, which is called Newton-Raphson scheme. So basically, it's still gonna use some gradient-like direction to update our model parameters in each step, but we're not gonna use the original gradient. Instead, we're going to do some projection or transformation of the gradient to better leverage the geometric structure of the likelihood. So how can we do the transformation? We're going to calculate the Hessian matrix of the objective function. Here will be the negative log likelihood. So then we multiply the inverse Hessian with the original gradient. We use that as our descent direction to update model parameters. So this is called a second order method because it has one order of magnitude faster convergence than the gradient-based approach. The gradient-based approach is called steepest gradient descent, which is actually not very, very efficient. If you want to faster convergence, usually you multiply some positive definite matrix with the gradient to accelerate convergence. One choice will be this Hessian inverse. But regarding why it is converges faster, why it can give us a better convergence rate. This is a content optimization class we're not gonna cover, but we would like just to give you this idea. It's called Newton-Raphson scheme. Okay, let us to illustrate how do we obtain this Hessian matrix and why it is called iterative related least square. We can first apply this Newton-Raphson scheme for the linear regression case. And then we move to the logistic regression and you see why it is called weighted least square. So if you look at the linear model for regression, right, the negative log likelihood will have this form. It's much nicer form, which is just a square loss, square loss over the training observations. If you take the gradient, it will give you a form like this, which I'm not gonna show how to do that. I believe everybody feels this is pretty easy, right? And this is phi again. It's a design matrix, right? Now to calculate Hessian matrix, we want to apply the Newton-Raphson scheme. So we need to calculate Hessian matrix of the objective, right? That means you have to calculate the gradient over the gradient again, because the gradient is just a function of W, right? The second term is constant W, right? So if you take the gradient with respect to W again, your Hessian will be just here, right? It will be just the phi transpose phi. So now we just apply the Newton-Raphson, right? So you just multiply the inverse Hessian with the gradient of our objective. You know, you just substitute those guys for H and this guy for E. You're gonna cancel a lot of terms, and finally it will give you this. What's that? If we directly solve this, meaning that I'm gonna directly find which particular W is a minimum of this objective function. That means I can get this gradient, right? I can get this gradient, I can solve this gradient to be 0. If you solve it directly, for W, it will give you this. So the takeaway is that for the least square case, doing one step Newton-Raphson update, you can get the global optimum. So that gives you a sense why Newton-Raphson is so is more efficient than the standard gradient, right? If you can also use some standard gradient descent approach and change the step size and iteratively to update, it won't be able to give you the optimal W by only performing one gradient descent. But if you do Newton-Raphson update, just one step, it has already arrived the optimal. Yes. Yeah, of course. There's no free lunch. Yeah, for Newton-Raphson, yeah, because you have to compute the inverse Hessian, it is actually not very practical for a large model with a lot of parameters. That's why there are a lot of approximation method of the inverse Hessian. Like maybe many of you have used this before, like LBFTS. How many of you have heard of it or used it before, LBFTS? Right? The key idea is just to approximate the Hessian with some low rank matrix. So once the
this method you mentioned the homework to optimize the likelihood.
You mean homework 1? I don't think homework 1 I asked everybody to use. I asked everybody to use LBFTS to optimize. Yeah. But you don't need to implement LBFTS. You just use some library to do that. I just want to give you the sense what does LBFTS actually is doing. It's actually try to approximate this guy and to transform the original gradient into accelerate the convergence. Okay, now let us switch logistic regression, right? And want to do the same thing for the update of logistic regression. So this is a negative log likelihood. We want to minimize the negative log likelihood. This is our gradient, right? So if you further compute the gradient of the gradient, which ends up with a Hessian, it will give you this form. This is not in the linear regression case, is simply phi transpose phi. Phi here is design matrix. Here you have to incorporate a diagonal matrix R, where each diagonal element is your predictive probability times 1 minus predictive probability. And it's kind of like a strongly related to the form, the Hessian form of the linear regression, but there's difference. The difference is that you have an extra diagonal matrix R, where each diagonal element is your prediction probability that the example to be 1 times 1 minus that probability. So you can see that actually R is dependent on the current model parameters W, right? So that means the Hessian matrix is no longer constant. For the linear regression, because it's phi transpose phi, once your data set is there, this is fixed, right? Hessian is fixed. But for logistic regression, because your W is updated each step, right? That means your R is different. That means your Hessian is changing as well. That's why we call it iterative procedure. And then if we just apply the Newton-Raphson update, H inverse the gradient of the objective, it will give you some manipulation. It will give you the form in this way. Right? So this is a Hessian. Right? Remember, it's a Hessian, and this guy can be viewed as a adjusted responses. Right? Z here is the prediction score from the previous W subtracted by R inverse and the difference between your prediction of the probability prediction and the observed response. So of course, because Z is dependent on W as well, so Z is changing along with updates as well. So that's why it's called updated response. But each update, if you will, there's R times Z as a special type of response, okay, for the linear regression, and you will this guy as a special type of or kind of adjusted design matrix for the linear regression. So each step is actually an update, one step update for the corresponding linear regression problem. That's why this is called an iterative related least square. But you cannot do it in one step because every time your R and Z are changing. You have to update your W and then update your Hessian, update your updated response, and then do this update until convergence. Even so, this is quite fast, like, as compared with the standard gradient-based approach. Okay. Any question? All right. And then we can extend logistic regression to multi-class logistic regression. So suppose we have K classes, right? C1 to Ck, right? And of course, we have to make a prediction. Right? To make prediction, we need to we need to calculate score for the prediction for each particular class. That means we have to introduce the K weight vectors. So for each class, I mean, given the same input vector, we're going to calculate score AK. And then we model the probability. This instance take class K as the softmax function of those scores. So what is softmax function? It just takes exponential of each score and then normalizes. This is called softmax. So when you say, like many neural network libraries, right? When they do the image classification usually refers to quite a large number of the classes, right? So you want to assign a probability for predicting of each particular class. So they always use this kind of softmax as the modeling of the probability for each class. So you got some prediction score, which can be arbitrary number, can be -10 or 100, okay? And then we take exponential of them to ensure the positivity, and then we do the normalization to ensure, okay, that it will give me a probability. And by right now, we see that the probability of each particular class K will not only depend on the score for this particular class. It also depends on the score of other classes. Why? Because they are in a normalizer, right? They're in a denominator. So that means when you calculate the gradient with respect to those weights W1 to WK, right? So I have to compute, you have to consider both the denominator and the numerator. Numerator and denominator. Okay? So here is the general result. So YK is the probability that you take class K. So if we calculate the gradient of the probability YK with respect to AJ, it will give you this form. So J can be K or not K. So when J equals to K, that means, okay, how does it what's the derivative with respect to the score of taking class K? Like if J is null K is the score for other classes. So you can see that this is essentially related to a identity matrix. If K equals to J, then IKJ is simply 1. If K is not equal to J, the off-diagonal elements in this identity matrix is simply 0. So this is also a known result from the multi-class classification. And I suggest you guys to derive it. It's just a practice of calculus, nothing else. Again, if you want to perform maximal likelihood estimation, suppose we have observed n data points, right? Where each data points, the output, remember, we talked about that for multi-class cases, we use one-hot encoding to represent the label. That means if you take class 1, we have one element as non-zero, and all the other elements as 0, right? If class K, that means the second element is 1, and all the other are 0. Right? And then we can write down the joint probability in this way. Right? And it's just a product of n likelihood. And for each particular likelihood, it's just a product of exponent of each probability to the power of the elements in this one-hot encoding. Right? That means for any particular element who is 1, the corresponding probability is selected. All the other probability will simply preempted because their power is simply 0. So again, we can use Newton-Raphson updates to estimate the parameters for the multi-class logistic regression. And this is the gradient of the negative log likelihood. And if you take the Hessian, it will give you this form. Again, we're not gonna show how it's derived. I believe everyone is able to replicate this derivation. I'll leave it as an exercise for you. So for binary classification, there is another approach. It's called probability regression. So probability regression is also a popular binary classification model as an alternative to logistic regression. So what is probability regression? Similar to the logistic regression, we still use a linear structure to model a prediction score. But the difference is that now we want to map this score to some probability, right? For your prediction of label C1, right? So now we're gonna use the Gaussian CDF to perform mapping rather than the logistic function. So the standard Gaussian CDF can use just the integral, right? Integral from this is a negative infinity from a particular number A. So in CDF function, we know that CDF function will be 1 from if we integrate it from negative infinity to positive infinity, right? So if you have a finite upper bound in the integral, it will always less than or equal to 1, right? And also it is always bigger than or less than is always no less than 0, right? So that means this Gaussian CDF, standard Gaussian CDF, will always give you a valid probability. That is a probability. That is the probability regression. The only difference is in how do you choose this score mapping. You need to map the raw score to some probability. Logistic regression just uses logistic function or Sigmoid function, and probability regression uses the Gaussian CDF. So what's the difference? The difference lies is in the behavior of this mapping function, or sometimes we call it a link function. Right? So this blue curve, this green curve corresponds to logistic function, and the red curve corresponds to the Gaussian CDF. So you can see that although with large input, both is bigger than or equal to 5, right? Both logistic function and probability regression is just you can view them almost as 1 or 0, right? But in the range between, right? In a number of input in between, they are different. And probability regression actually is a little bit has a stronger truncation effect than the logistic function in that. Okay, you can see that even for the input, which is relatively small, the probability function will give a value closer to 1 or 0, right, than the logistic function. But why do we use probability regression? The probability regression has a very nice or convenient advantage in performing Bayesian modeling. Why? Because it's equivalent to a fully probabilistic sampling. That is, we can introduce a latent variable z. You sample z from some Gaussian distribution with the mean of your prediction score. Prediction score is W transpose phi, right? And with the standard, with the variance to be 1. Then you generate the label according to the sign of this latent variable's value z. Okay, so that means if z is less than or equal to 0, you just predict the label 0. If z is non-negative, you just predict label to be 1. So if you just marginalize out z, it will give you the original probability regression model. That means if you want to do Bayesian inference, we can augment our model with this z, right? Because you have a Gaussian prior with z, and given z, you will have this step distribution. So the posterior distribution is relatively easy to calculate. And even you see that it's essentially truncated Gaussian. It's much easier for the posterior inference. But for the logistic regression, actually there's no analytical form of the posterior distribution. You have to do some kind of approximation. That's why like probability regression is also very popular. We'll get to this. We'll get to the calculation detail about how to obtain the posterior distribution of the model parameters for logistic regression and probability regression later. And you see the point I mentioned here more clearly. But right now here, I just to give you a sense. And finally, I want to introduce another type of multi-class classification. That means those class labels are ordered. It's not like you can just ignore the order. For example, if you want to rank, you want to predict the rank 1, 2, 3, 4, right? We only need a finite number of ranks. That means it's a multi-class classification. But those class actually they have orders. Right? You cannot say 2. You cannot put 2 in front of 1. Right? You cannot put 3 in front of 2. Right? You have to consider their ordering information. So in this case, we call this problem not just multi-class classification. Instead, we usually call it ordinal regression. So we have K classes where these class labels, where these labels have an ordering relationship like C1 less than C2, blah, 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 less than CK, right? So for example, rank or disease progression, like Alzheimer's disease, you have 3 stages, normal, mild, cognition impairment, and severe, right? So this progression, of course, has some ordering relationship. Right? So in that case, if you simply use multi-class logistic regression, it's not a problem. So how do we encode the ordering relationship into the model, into our modeling framework? Right? We're going to use this multi-class probability regression. Because logistic regression actually is not the multi-class logistic regression is not very natural. We consider probability regression. How can we do that? Like, we partition the real domain into some ordered regions. Right? So we have this line. So of course we can partition them into several regions. Definitely these regions can be viewed as some order. Right? This is B1, B2, and B3. So this is BK. So we're gonna map each region to some ordered class. Right? How can we do this mapping? Right? So suppose we still have this score, A equals to W transpose phi, right? And following the probability regression model, we know that it is equivalent to first sampling a latent random variable Z. Okay, and then we just check which region Z falls in. Okay? If Z falls in this the region K, we're gonna output the corresponding label K. Because the region which it falls, those regions are ordered. So the corresponding labels are ordered as well. In this way, we naturally extend the probability regression to multi-class case, at the same time preserve the order information. That's why that's another advantage of using probability regression, because it can easily encode the ordering information, which are important in a type of applications. Okay, let's stop here today. We're going to wrap up generalized linear models on Thursday, and then we're going to talk about graphic models. Yes, exactly. I mean, usually we don't optimize BI, but in some papers you will see that they're going to optimize BI as well.